Another big cosmological question. Do you think the Earth revolves around the Sun, or do you think the Sun revolves around the Earth? This was actually one of the great debates in the history of science, and had I asked you the question 400 years ago, you'd have been well advised to think carefully before answering. In the year 1600, Giordano Bruno, an Italian philosopher, was burnt alive by the Catholic Church for his heretical views, prominent amongst which was the idea that the Earth might not be at the centre of the universe. In the ancient world, the prevailing view was overwhelmingly that the Earth remained motionless at the centre of the universe and everything else revolved around it. This is how it looks. If you stare up at the sky, it appears that everything moves around us, and it was always going to take pretty compelling evidence to persuade people that this might just be an illusion. There's also perhaps a psychological element. In The Hitchhiker's Guide to the Galaxy, Douglas Adams imagines a device called the Total Perspective Vortex, which, if you enter it, reveals to you just how insignificant you are in the context of the whole wide universe, with the result that your mind is destroyed. And I think we do have this inner need to feel significant in the scheme of things, and this too would have led people to favour the geocentric model, which places the Earth at the centre. There were dissenters, however. Around 250 years BCE, the ancient Greek Aristarchus wrote a book in which he gave the sun the central role and proposed that the Earth both rotated on its own axis and orbited around the sun. Unfortunately, the book has been lost, so we don't know what detailed evidence Aristarchus based his model upon. What we do know is that not many people at the time were persuaded by it, but it did at least get them thinking about the problem. And so the ancient Greeks asked the question, how would we know if the Earth was moving? If you were stood at the equator, rotation of the Earth on its axis once in 24 hours would mean that you would actually be travelling through space at around 1,000 miles per hour. Surely, you might think, you'd know if you were travelling that fast. But think about your experience on a plane. When you're taking off, you're very much aware of the acceleration as the plane builds up speed on the runway and you're pushed against the back of your chair. But once you're cruising at high altitude, then so long as the air is clear and you're not getting a bumpy ride, you're actually got pretty much no sense of motion at all. The point is that what we're sensitive to is not speed, but acceleration, meaning changes in our speed or indeed in the direction of our motion. So we would only be able to detect the rotation of the Earth if that acceleration was big enough for our bodily senses to pick it up. Now, as the Earth rotates, its speed remains constant, so that's not going to be detectable, but the direction is constantly changing. That's what going round in a circle means. But if you think about it, because it takes 24 hours to complete a revolution, the direction is changing only very gradually, and our bodily senses are not good enough to pick this subtle effect up. What the ancient astronomers also realized was that if the Earth were orbiting the Sun, then at any particular moment we ought to be moving towards some stars and away from others. And they reasoned that those we were moving closer to should be separating further apart in the sky, while those we were leaving behind should be clustering closer together. They made the most accurate measurements they were capable of and discovered no such effects as the year went through its cycle. And they concluded, therefore, that the idea that the Earth was orbiting the Sun, as set out by Aristarchus, must be wrong. What they couldn't have known then was that the stars are just so far away that the difference in the distance from us to them between one side of our orbit and the other is totally negligible, and these effects are therefore far too small to measure with the technology that they then had. So we have to give those ancient Greeks credit. They did look for scientific evidence, and they used it to come to a rational conclusion. It was only when a deeper understanding of physics emerged much later in history that their arguments began to look dodgy. And there's an important lesson here about science in general. You can never sit back and say, right, that's that problem nailed once and for all. Always have to be willing to reassess what you thought you knew in the light of wider advances in understanding. The biggest challenge for the geocentric theory, in which everything moved around the Earth, at the time actually seemed to be to account for the movements of the planets in the sky. If you look up night after night, you see that the planets move against the background of the stars. In fact, the word planet means wanderer for this reason. Ancient astronomers mapped these movements very carefully and used them to try to construct a model of planetary motion. And what they came up with was that the planets appeared to be executing a strange and intricate dance around the Earth, in which each planet would constantly be twirling around in small circles, which we call epicycles, at the same time as gradually making its way around the big circle of its orbit. It was a very strange picture, and they had no idea as to why the planets might behave in this way. But it was successful in the sense that it could account for the observations in the sky, and indeed successfully make predictions of how the planets would move in the future. As time went by and more accurate measurements of planetary positions were made, the model had to be tweaked to fit the data, and it didn't reach its definitive form until about 150 AD. The Egyptian astronomer Ptolemy came along. His version of the model then remained pretty much unchallenged for an astonishing 1400 years. This was partly because it was actually very good at predicting how the planets would move. But it was also because, in Europe at least, science pretty much went to sleep during the Middle Ages. Learning the truth about the universe during those long centuries consisted essentially of just checking what Aristotle had to say about it and deciding you agreed with him. When a serious challenger finally emerged, it was a Polish astronomer called Nicholas Copernicus in the 16th century. His objection to Ptolemy's theory was not actually really a scientific one. It was his belief that a correct theory of the universe ought not only to be successful at modelling the data, it ought to be beautiful. And he thought that Ptolemy's theory was just messy. Copernicus was drawn instead to a model whose symmetry and simplicity appealed to him, in which the Earth, along with all the other planets, moved in simple circular orbits around the central sun. And he realized that if the Earth was moving faster than the planets outside it, then periodically it would catch up with and overtake these outer planets. And as it did so, those strange looping movements that the planets formed in the Earth's sky would arise quite naturally. No need, he thought, for those epicycles which had made the systems devised by the ancient astronomers so messy and complicated. In the end, though, Copernicus was faced with two big problems. One was that by this point in history, the Church had decided descriptions of the Earth contained in the Bible were to be interpreted as meaning the Earth was at the centre of all things, and any other model was therefore likely to be seen as heresy, and Copernicus just wasn't keen on the whole burning at the stake thing. His second problem was that his model didn't actually work very well. Although qualitatively it seemed to answer those questions that bothered him about why the ancient model was so complicated, but when it came to actually fitting the data, it didn't cut the mustard. And tragically for him, he had to reintroduce epicycles into his model in order to get accurate predictions of planetary motion. So it seemed that what he had created was a dangerous failure, and he hesitated for a long time to publish it, but in the last year of his life he did so. There's another important general point here. Many, perhaps most, bright ideas in science in the end don't lead anywhere, and plenty of experiments simply don't work. But it's important that scientists still talk about them, partly just to spare others from wasting time going down the same blind alleyway, but also because sometimes what they've done may be almost right, just not quite, and all it needs is a fresh pair of eyes and a fresh brain to have another look at it, maybe tweak it a little, and that breakthrough might still come. And that's how it was in this case. Half a century after Copernicus published, a young German astronomer called Johannes Kepler came along, read Copernicus' book, and was immediately a fan. He tried very hard to get the theory to fit the data, but nothing seemed to work until he let go of one crucial assumption. Kepler ultimately realized that the problem was the circles. Copernicus had insisted on circular orbits because their symmetry appealed to him, but there was no actual evidence to say that had to be the shape. Kepler allowed the circles to be stretched a little to form ellipses, and suddenly everything clicked. Kepler's new model, with the Sun in the middle and all the planets, including Earth, revolving around it in elliptical orbits, was every bit as successful as Ptolemy's model at accounting for planetary motions. So now it's decision time. Who was right, Ptolemy or Kepler? One way out of this, which will appeal to you if you like to avoid a fight, is to say, well, they're both right. Around the same time as Copernicus was wrestling with his heliocentric theory, over in Italy, Galileo was explaining to the world that all motion is relative. In other words, you can't just say, I'm moving. You should say, I'm moving relative to you, but then it will be equally true that you're moving relative to me. On that basis, we could argue that both models are equally valid. And mathematically, that's true. All you're doing when you switch from Ptolemy to Kepler is to describe the same motion from a different fixed reference point. There is a problem, though, which we can illustrate by imagining a simpler experiment. Let's say that you'll run in circles around me 100 times. At the end of it, you could argue that from your perspective, it had been me who was moving in circles around you, but you'd have to wait till you got your breath back and stopped feeling nauseous to do it. So what's clear from that is that although mathematically it would be equally valid to describe it from either perspective, from a physical point of view, there clearly was no such equivalence. So really, we can't take this easy way out. A second approach, and this is very much what scientists' instinct usually is, would be to say, well, let's look for more experimental evidence. And by the time Kepler published his model, that evidence was actually already there. Nearly a century before, the telescope had been invented in the Netherlands, and when Galileo heard about it, he built one of his own and used it to look at the night sky. He saw things that persuaded him, at least, that the heliocentric model was right. First, he saw that Jupiter had moons. He tracked their motions from night to night and realized that they were orbiting Jupiter, not orbiting the Earth. So the idea that the Earth was at the center of all these motions clearly was not right. Even more importantly, when he looked at Venus, he saw its shape changed from night to night. It went through phases, just the same as those that we see for our moon. And when he thought about it, he realized that this is exactly what you would expect based on the heliocentric model, but could not be explained by Ptolemy's model. The church responded by locking Galileo in his house and threatening him with torture if he kept banging on about it, but still, the evidence was there. So Kepler has the weight of observational astronomy on his side. So far, though, if you think about it, everything we've talked about has been addressing the how do you know question. And we haven't really thought at all about why. Science, remember, is supposed to be about not just describing, but explaining why things happen. And neither Ptolemy nor Kepler had done that. What the world needed now, as he himself would have been the first to point out, was Isaac Newton. In 1687, Newton published his great work, the Principia Mathematica, in which, amongst a whole load of other things, he set out his theory of gravity. Newton realized that the gravitational attraction between the sun and the planets would be the key to the way they moved. And so he derived equations based on his gravitational theory, which would predict what planetary orbits should look like. The conclusion he came to, interestingly, was that neither Ptolemy nor Kepler was completely right. Neither the Earth nor the Sun, according to Newton's equations, remains completely motionless as they orbit. Rather, they each move around their common centre of mass. If you imagine a line drawn between the middle of the Sun and the middle of the Earth, the centre of mass is the point at which there's an equal amount of mass to either side. But because the Sun is so much more massive than the Earth, this point actually is deep within the heart of the Sun. And so, to a very good approximation, what Newton's theory shows, quite independently of the observations, is that the Earth does indeed revolve around the Sun.